Welcome to this video. In this one we're going to look at some of the advantages or some of the features of this circuit of mine. It was inspired by the Super Joule Ringer of Lasersabers. I think we're like 14 years down the road from when Lasersaber first did his setup, and this is sort of like a derivative of Lasersabers stuff. It is, if you check the schematic you'll see that it is different. However, it was inspired by, and there's one of my replications of Lasersabers work, and this thing was amazing, and I still use, as beat up and crappy as it looks, is very great for recovering batteries. It'll actually repair some of the batteries for many reasons. Some of the drill batteries and that sort of thing stop working, so that one there, have a look on my channel. You will see I covered this one in depth here, but one of the side effects or one of the negatives of the Super Joule Ringer is the ringing. It is just sometimes makes you feel like you need to run away screaming. It just gets inside your skull and seems to go to the deepest parts of your brain, and just, it's a great rat deterrent or a rodent deterrent. Like it just makes you feel horrible. And so whilst I used it for a couple of years as a main lighting source when I was off grid, I had normal conventional lighting sources, but they're very wasteful in the sense that you're running an inverter, you're running a 240 volt inverter in my case, just to run a couple of lights. Like, there's a lot of overhead just for the inverter itself, and it's not very efficient, and that's initially why I looked at the Super Joule Ringer. And just that noise just drives me insane. I mean, I went to the trouble of making a soundproof box for the thing because it just, I'd rather sit in the dark, to be fair. Don't get me wrong, I don't want to beat up on the Super Joule Ringer because it's the reason why I am where I am today in relation to this circuit of mine. So we're going to just have a look at a couple of quick things, and then I want to pull all of this apart just to give you a quick look of just the bare minimum, what's required if you just want a light and you don't want to get yourself bogged down in this alternative energy realm. Then you can just build yourself a light, and that could be a light that you just use locally, or it could be a light that you send the power through the earth and you could have it kilometers away. It's really up to you. On Tesla's paperwork, he talks about for similar systems, high frequency stuff, being able to transmit a signal all the way around the globe. Now, obviously, that's going to take a little bit more power than probably what you could obtain out of the battery, a little battery like that. But in my case, I am able to transmit over 130 meters through the earth and run a 240 volt unmodified bulb straight from the shop. So that's a 240 volt. This one here, 4 watt LED, so that's 240 volt. So that's just off the shelf. One of the things that I wanted to make sure is I could just do off the shelf components. I don't want to be modifying like in the early days of like the Joule thieves and that sort of thing. You would gut a CFL, an old compact fluorescent light. You gut one of those, take the electronics out, and just use the actual bulb itself. again, a lot of them had that high pitch ring, which just seems to drive me insane. Like, I got to send the cat away. The cat won't be anywhere near it. Same with the rodents; they won't be anywhere near it. So this, for me, like getting this to work silently, if you can hear any noise, mechanical noise or anything like that, it's not from this thing. Probably shouldn't get that device too close, actually. It's got a large radioactive field around it. So I'll give you a quick example. So we're going to look at the extra features that this thing has, and if you're someone that just wants a light, just stick around until the end. I'll try and make this one quick, and you can see what's required just for a light. So none of the fancy crap. All right, but for example, one of the special features about this circuit of mine is it doesn't respond in accordance with conventional electronics. So like if normally you place an extra load on a device like that, and on a conventional electronics device, place an extra load on top, it will naturally consume more power, a lot more power, and usually the rated volume or rated power value of the load that you're trying to run. So like this 1 watt LED should add 1 extra watt of power consumption to that system. So we got initially 5.5 watts, 5.6. Alright, so we put that in now and try and keep that in the screen at the same time. And you can see our top has now dropped. Oh, there we go, we got 5.6 again. Right, but it should have gone the other way. It should have been 6.6 now. So let's add in extra one. And they're just wirelessly coupled. And so now we've got, yeah. Okay, so 5.3, what's the top? 5.5. And the lowest I saw was 4.9. Let's add another one. Turn that way. Alright, so now we've just added 1, 2, 3. And we already had this guy running, but that was at 5.5, so where we first measured it, or 5.6 maximum. So we just add an extra 3 watts, and we don't see that showing on the meter. Okay, so I could also add extra coils, like somewhere here there's a little generator. There it is, a little generator coil, same as these little guys here, but got a full wave bridge rectifier and that, and I could put that on there and run a light off of that as well, and also see no increase. So it's a little bit bizarre in that sense. If I take this 6 watt light and I plug that in, I'll set that up there, and we'll take the cables for it, green being positive in this case, so we'll connect that down there to, I have one of Tesla's coils wrapped around there, just 9 turns of that coil, so we'll put that on there. And what we're looking at now, we've got say 5.3 watts. Plug this one in. Okay, so that's now working too. And what are we at there now? 5.7. So that saw a tiny increase, but this is a 6 watt light. It doesn't appear to be full brightness, maybe about 50%. So let's say that was 3 watts. Well, with the 1, 2, 3 there, and then this one, and then say that's at half speed, we got 3 watts there, and so we should be around 11 or 12, but we aren't. And then, so you would have seen, if you've watched some of my other videos, you would have seen me placing these Balin Ferrite suppressors. And these come out of electronics. You know, they're basically a radio or a noise suppressor. These are placed on a line to sort of dampen down any literal noise like static, electrical, stray radio signals and that sort of thing. But in my circuit, then now I've placed these on the positive line, and then these two here are on the negative line. It's all one wire. It comes in to each suppressor and goes around 4 times, and then continues on to the next suppressor 4 or 5 turns, and then this one is just a jumper lead, but I've connected it to the end of the wire coming out of the suppressor just to give me a slightly higher voltage. Again, these don't seem to have a normal reflection on the current draw. These produce a different type of electricity. It's really difficult to measure. So I'll show you, like, it has some strange behavior. So if we just connect it up like normal, so this bulb here is a 90 volt bulb. It's used as a signal indicator bulb, and it has a little resistor there so it doesn't blow up. And if I take that resistor out of circuit, we can see like why you have the resistor there, because that runs a little bit too hot, and that would burn out and shorten the lifespan of that little guy. So now that is an AC power that is derived from the DC line. So that's something that my circuit creates and then feeds backwards into the power lines of the actual circuit, and so the DC power supply lines, and so that is running through everything connected on those lines, and it runs back inside the battery. So it's really strange the way it behaves too, because I can disconnect it, and we can go, if I go close to the bulb, and that's glass, and I'm not electrically connecting anything, but just coming within range of it, and it's able to turn it on. So I find that really impressive. So if we now go, we'll stick that one on there, we'll go there so it's easier to see, and then what I'll do is I'll take it off the other end of the coil. Alright, and I will place this little alfoil tray, or it's a little pie tray, and I stuck aluminium foil on the bottom. It's going to be a UFO. I need to make it bigger if I want to get inside, but alright, so now this sort of acts very similar to Morey and the way he would extract energy out of a wire, sort of acting as an antenna. And so if we trigger the oscillations, I've connected up that 90 volt bulb via the wire, to the little UFO pie tray, and the other end is there, which is open, the end of that capacitor there, and so that's open circuit. If we touch that with the pie tray, and we'll get that light to come on, and although it might be dimly lit and wanting to go out, so one thing's always misbehave when you're trying to do a demonstration. They don't do what they did before. Okay, so that's gonna misbehave for me now. So I really should have had some more cables here so I could just demonstrate that properly. Oh, okay, it might be because this other light's running. So some things you're going to have to decide which features you would like of this circuit and take other parts away as they're not needed. So let's go back on here and see if we can get this jump started again. Okay, so it's wanting me to keep it in relative proximity. So you can see there, like, if I move it away, it goes out. I had it before, I'm not sure if I've done something different this time. I had it before where it was continuously lit. And there's so many configurations, I forget what I did, and then I get all excited and I'm like, oh, I've got to show that in the video, and then I forget. And so you may have seen some of this stuff before, but yeah, I apologize if I forget what I've already shown you and double up on it. Alright, so let's try so difficult with one hand to do this stuff. I know every YouTuber doing this says the same crap. So righto. Now I'll just demonstrate this bulb here is a 240 volt bulb and 40 watts. It's a bulb out of an oven. Actually, this is a bulb out of a microwave. But yeah, still 240 volts, 40 watt. That appears to be lit to around about 10 watts. So only a quarter of that. But again, let's just point out, so that's not right. Let's just disconnect this. Okay, and so we're looking at 5.7 watts. If I go connect, say it is only at a quarter and it's only consuming 10 watts. If I connect a 10 watt load, alright, going on now. So that's just not right. It's just not right. So could you get to a point where these suppressors, ferrite suppressors, are actually not consuming your energy, but in actual fact supplying more energy or reducing the load? And so because they aren't reflecting directly on that load, how many of these can we put in place? I kept going and trying to get a brighter light bulb, so you may need a few more than these. This is all I've got. And we've also got this light running here too, which is just on a different ferrite suppressor. So we've still got those lights running. We're still at the wrong wattage. Let's put this in. Now this is the 4 watt LED, so we'll screw that in, and you can see with me loading up this light, like that's taking the power, and this light here isn't coming on. If I remove these ones, we'll take away some of the glare, and then we'll be able to see that light is actually on, but it's just barely on, and that's because this one here is taking most of that power. But where is the power coming from? Because we were already consuming more power than this, and now we're taking extra power and it's not reflecting. And so I just find that really interesting. Now if you want your light, low level light, so I just disconnected that there, so that's just open circuit now, so that would be low beam. And then if I short out these Balun suppressors, so I place this end coming off the cap and I place it directly on the positive line coming off the other end of the suppressors, watch the light. Ooh, okay, so that's considerably brighter. Right, so I imagine we'll see a massive jump in wattage. But not so. Okay, so if you just wanted a light, you could do away with all of this other stuff and just use a single Balun suppressor and just a dead short on it. And there we go, that will give you 240 volt light bulb, nice and bright, lasts for hours and hours and hours, because something it's important to understand, the power that's placed inside these DC lines goes all the way to the battery, and so there's a high chance that that's also charging it, and that's what keeps the high runtime, it keeps the long run times going. So now that's not the only thing you can do. You can also take this Balun Ferrite suppressor, it's a mouthful, and place it on a coil like this one. Okay, so this is just a toroid, and again, because we're creating a dead short, the light increases intensity, and we go from 7.1 watts to 6.9, so barely a movement, but it definitely is less current, and we've got more power output. So again, not what they bloody taught us in school, is it, kids? Righto, so we'll place that on there. Oh, actually, before I do, I'll explain what that's connected to. We've got a toroid there. It's basically a 2-to-1. We got twice as many turns on this side, so the power goes into this side. Clearly it's AC, otherwise if you were short a DC connection like that, then you would not get any power out of here. No way, not at all. So now I've got that feeding into full wave bridge rectifier, and then into a large cap. That's a welding machine capacitor, so it can take a decent hit. I'll show you that in a second. And then the output of that cap is fed into the solar controller unit to prevent overcharging. If you just leave these things on their own, they could be a problem. So that prevents overcharging. And so I'll connect up the other side of this coil, and we'll see if it actually starts to charge. So we can see on the screen there, on the what would be the left hand side of the screen, if I turn it like that, there's no indicator, no solar panel. And so if I connect up this coil now, so we get our brighter light, and we also start charging the battery. Right, and our power consumption has done what it did before and dropped, even though we've got a more intense light. We can add back these lights, and the one thing you'll notice is the flux changes depending on what type of load you're running. So that frequency changes, and then sometimes these lights may be dimmer or brighter. Like this one down here is now gone dimmer. So they are all affecting one another, but not in the conventional values. So we should, like I said before, we should be seeing massive increases, if not double the wattage that's being presented there. Alright, so we know if we do that, we can feed back to battery and we can charge it. Now, one thing I'll say about this is if you're going to start messing around with the capacitors like I'm about to show you, extremely lethal. What I want to demonstrate here is its capacity to rapidly recharge. So if I take off this wire here and that wire there of the capacitor, I'll put that over there, and I take off the corresponding wire from that coil, the green one there, which I should really use as for my chicken stick for this next demonstration. We'll remove the back to the capacitor wire. Alright, so that capacitor is on its own now. We will leave this red jumper on here, and that will be going on to there as a dead short. Now, if I connect up these Balun suppressors to this coil, again we get the massive increase in brightness. Okay, and what happens to the current draw? 7.1, and it reduces it again. So again, not normal, right? And now we've got a capacitor that can be lethal and will load rapidly. So what I'll do is I'll remove this positive line and I'll place it back on quickly, because it will rapidly achieve a very high and dangerous voltage. Oh, okay, one of the leads has come off here. Okay, because I'm thinking to myself, so even though it only has one side, it's still able to charge up. Yeah, so don't like just terminate one terminal and think you're safe. That's still going to charge up to a dangerous value. But watch the speed at which it happens now. Okay. Yeah, boy. Sometimes I feel like a kid when I'm doing this. I'm just like, it's super dangerous. Be really careful. Normally when I do this, I use a chicken stick, or just a piece of wood, so I'm not holding the wire. But you can see how volatile it is, how quickly it charges, and how little power it takes to obtain this. It's just so bizarre. It does not behave like normal juice. Alright, so this video has already taken way too long. But there you go, kids. That's how you can be dangerous. Please don't try this at home. This could take your life. So if you just want a light, now I'm going to pull all this part. I'll move it out to a desk where it's clearer, and then we can clearly see how easy it is. Just if you just want the light, you just need a light, or you need a light to run it out into the paddock or something. They make great garden lights, like a garden light that actually works. So yeah, alright, On to the next bit. So here she is, just the bare basics. We have one battery, 12 volt. What is that one? That's an 8 amp hour. And that will make just the normal light, the 4-watt bulb. That'll make that run for around about 10 hours. With no feedback, no special tricks, no anything. So 10 hours. I've left that little Balun suppressor on there just if we can see if at this frequency it still works. And so realistically, aside of the light bulb, the only thing you need for this is wire and one transistor, a 2N3055. Have a look at my channel. I've got full tutorials there on how to make this exact unit. What wires go where, and I do them one by one, and so there's no confusion. It still looks messy, but the reason for this wire harness sort of setup here is to get the aluminium away from the coil. And I've said this before on my other videos. The aluminium pulls down with eddy currents, pulls down on the coil's magnetic field and reduces its strength. So you want that a certain distance from it, not too far, because then you start to run into capacitive issues with the wiring. It changes the tuning of it. So I usually place like a 10 to 15 centimeter lead out of all my coils, so just to be 10 to 15 centimeters coming out on every wire, so that the wiring setup can be away from the coil. Then if you just want to run the light into the ground, it's a simple case of taking off of the positive and negative lines in there in the terminals, or you can do it on the strip here. And one goes into the ground, and then the other one goes into a light bulb before going into the ground. And it doesn't matter, you can have it on either one of those wires leading into the ground, and then that will work according to Tesla, unlimited distance. Give you an idea, like the further you go, the more amperage increases, and the normal assumption, every time I spoke to someone when I was researching this, they were like, oh, you can't do it, oh, the ohms go through the roof, you have so much resistance, your amperage will just run away with itself, and you'll have the thing not work, not even begin to work. Well, it's completely the opposite. The thing works so bloody well that you just don't even really need good earth rods. Like the earth rods that I use are just old cattle fence posts, and the piece that goes into the ground's like no longer than 15 centimeters. So yeah, it does get brighter if you put in proper real copper rods or water pipe or something like that. It does get brighter, but that's all you need. So that's the basics. If you just want a light, one transistor costs you $1. Okay, so, and then the light bulb is probably the most expensive part, aside of the battery. I mean, you can use lead acid battery. This battery is a lithium battery. It doesn't really matter. The lithium, however, if you're trying to recharge and that sort of thing, and keep in mind that there is that current flowing over these DC power lines that is going into the battery too, while the light's running. So you can make sure that those are the right length to increase their ability to pick up the radio transmission that's coming from. from the battery. So if you want to bother and you want to make it run for longer periods of time, the length of the power lines going to the circuit should be either quarter wave or half wave resonance of the secondary coil in there. So yeah, if you get an ohms reading of the secondary winding once you've wound it, then you can make that make the leads a divisionary of that. So just divide it by 4 or divide it by 2, and then you can divide by any number as long as it divides into itself, just so that you keep that resonance. So go for probably divided by 2. Oh no, divided by a quarter. Those would be too long. So divide these lines by a quarter of the length of the secondary winding inside the main transformer. So this is information that Don Smith gave us, and if you look through Don Smith's videos, you'll see these transmission lines, DC transmission lines that he had were stupidly long. He had like this really long cord that he would pull out for his demonstrations, and everybody's like, what's with the big ass extension cord? Well, that was an antenna, that cord. So because this produces a radio frequency, the length of the cable is determined by the length of the secondary. So the length of the DC feed lines is determined by the length of the secondary, and you just make it a quarter of that, and you'll get it much more efficient. Or not, or you could just go, bugger it, I can't be bothered, I just want a light, mate. So just do that. Alright, so I'll connect this terminal on. Again, we've got one transistor. You need the heat sink, otherwise it's going to get a little bit warm. It can survive without it, but you'll start to melt the plastic of this terminal strip. Okay, so here we go. Circuit's on. Now I can't tell you obviously how much it's consuming because I no longer have the meter in place. So there are many different positions that you can run these little wireless lights. Like work in the center. If you imagine around this coil, it's a toroid. So you've got field lines coming out of the top of this thing. They wrap around and they come back in through the bottom. Okay, and that's at every angle. So this way, that way, that way. Really hard to show, but yeah, imagine a donut, and the energy field is like that all the way around. Okay, and you can see that when you start putting this little coil. You can see that if we move out here, like we're off the edge of that donut there. However, if we turn it, turn it there, you can see that it's still within the circle of that. So here, the magnetic flux is running vertically, like, well, in the donut, in the toroid shape, but moving up and down. So placing a coil this way does nothing, but placing the coil that way obviously allows the flux to go through the coil. We want the flux going through the coil, and you need to therefore position it so here the flux is coming out of the top and coming around. So we can place the light like that, and it goes through the coil, through the center of that PVC form like that. And then as it comes around here, it's the same deal there. So again, if you turn it that way, if we turn this coil like that at certain positions, it's now leaving the field. But if we rotate it so that it's, you can see there, so it starts to have the field going through it again. So it's pretty straightforward. Alright, so let's put that back. Put that back on there. And we get the light bulb. Alright, let's screw that in. And there we have it. One 240 volt light bulb, run without an inverter, run without any modifications, and you can either just run it like that, run fine for like 10 hours, or maybe feed feed those wires into the earth, and you can run it a couple of miles away if you've got enough wire. Obviously you only need one wire if you're doing that, one long wire. So if you had a fence, for example, you could attach one output directly into the ground right next to the circuit. The other output goes to the fence, and then run that as far as you want and put the light bulb there, attach the light bulb to the other end of the fence and plug it straight into the earth. How bloody awesome is that? So yeah, my recommendation is build one before it's an issue, because you can do this so easily and you can just have it on standby. The amount of times we've had blackouts and that sort of stuff, and you're just like, well, this is the only place it's going to have a light on. So you know, you can do this. This is super simple. I know even this looks a little confusing, but like I said, I do have a tutorial there, and you could make this into a smaller form. It doesn't have to be on a 3D print spool. If you look at the diameter of that coil, the internal diameter of the 3D printer spool is around about 5 centimeters, so 50 mil hole. So therefore you could wind this on a piece of PVC pipe, 50 mil gauge pipe. You easily wind that on there. Obviously the wire will build up, but you just use tape on it to hold it in position, and it only comes out probably 3 centimeters in thickness, the entire, both coils, primary and secondary. Alright guys, this has been a long, I don't know how to make short videos. I don't think I can do it. It just doesn't seem possible for me. Maybe I just bullshit too much. I don't know. Let me know what you think. If you need any help, I'll try and get back to you all, and make sure I can give you any advice that you may need. Alright, thanks for watching. Please like, share, subscribe. Have a nice day.